Hello, and welcome back to Educator.com and our series on AP Computer Science. The subject of today's lesson is recursion. We'll first talk about what recursion is and how it's useful to us in writing computer programs, and then we'll look at a couple of classic recursive algorithms, one that calculates factorial numbers and the other that calculates Fibonacci numbers. We'll then talk about other applications of recursion and the type of recursive questions that you might see on your AP Computer Science exam, and then we'll talk about some important considerations when using recursion or deciding whether to use recursion. Recursion simply is when a method calls itself. Any method can call any other method, including itself. And when a method makes a recursive call, meaning it calls itself, it must call itself with a different value than it itself was called with. Recursive functions must take at least one parameter so that the value can be changed from one call to the next. And a recursive method must contain a conditional statement, such as an if statement, that will eventually cause it to exit without calling itself again. If the only thing your recursive method does is calls itself again, the program would never end, and we call that an infinite loop. And eventually you just have to kill the program if it's running in an infinite loop. So to prevent that from happening, we want to be sure that we have a case that causes the method to exit without calling itself again. And such a case is called a base case. The logic of the method should be designed in such a way that the values that are passed to the recursive calls change in the direction of the base case. So if our base case is when the value passed into the method is 0, we want the method to call itself in such a way that the number that's passed to the successive calls to itself is decreasing from whatever value was called initially down toward the base case of 0. Alternatively, if your base case is a large positive number, you would want the direction of the numbers that are being passed to the recursive calls to be increasing towards the base case. Most commonly, the base case is going to be either 0 or 1. So you would want the numbers to be decreasing. One of the classic examples of a recursive method or a recursive function is calculating factorials. And the factorial of a non-negative integer is defined or denoted by an exclamation point after the number, and it's defined as follows. If n equals 0, then n factorial, meaning 0 factorial, is defined as 1. Otherwise, for all n greater than 0, n factorial is defined as n minus 1 factorial times n. A recursive implementation of the factorial function in Java is shown here. We have our base case. If n is equal to 0, n is the integer value that's passed into the factorial method. And if that is equal to 0, we're simply going to return 1. That's this case here. For n equals 0, n factorial is 1. Else, if n is greater than 0, we're going to return n times factorial of n minus 1. And that is the other case here. N factorial equals, we call recursively the factorial function with n minus 1. So whatever n was on that call, we decrease it by 1 and call factorial on that number, and then multiply that result by the current value of n. So that is shown here, n times factorial of n minus 1. And we return that. So let's trace through a simple calculation of 4 factorial, and then we'll see this running in Java in an actual program. If we have 4 factorial, and we would call factorial with a value of 4. N would be 4 on the first call. we first check if n is equal to 0, and in this case it's not, so we do the else part, and we return n times factorial of n minus 1. n is 4, so that's here, and then we call factorial n minus 1, which is equal to 3 factorial. So we've decomposed 4 factorial into 4 times 3 factorial. We don't know what 3 factorial is yet because we've simply made another recursive call to the factorial function. So 3 factorial, we come in here, n is not 0, so we do the else part. We return n, which is 3, times factorial n minus 1. That's where we get our 3 times 2 factorial. We're not done yet because we don't know the value of 2 factorial. So we call factorial from this recursive call, factorial of 2, we get 2 factorial. N is still greater than 0, so we do the else part again. We return 2 times factorial of 2 minus 1. So that's 2 times 1 factorial. 1 factorial, we come in here, n is 1, n is still greater than 0, so we do the else part again, and we return 1 times factorial of 1 minus 1, or 0. So that's here 1 times 0 factorial. Then 0 factorial, when n equals 0, now we finally do the if part. N is equal to 0, so we simply return 1 for the value of 0 factorial. So after all of these recursive calls, then we are able to determine that 4 factorial is equal to 4 times 3 times 2 times 1 times 1. And the calculation is at this point complete. So we called 4 factorial, it called 3 factorial, and it called 2 factorial, it called 1 factorial, it called 0 factorial, and finally we've reached the base case of n equals 0, in which case we simply return a number 1 and don't make another recursive call to factorial. Therefore, the execution eventually stops. So let's take a look at the factorial function in Java. Here is the same definition that we showed on the previous slide. Here's our base case. If n equals 0, return 1, else return n times factorial minus 1. So that's exactly the same code that we saw on the slide. I'm going to call the factorial function from my main method down here. And I just have a simple for loop that's going to go from I equals 1 to I equals 10. Normally I use less than for the comparison in a for loop, but I do want to include 10, so I'm doing less than or equal 10, incrementing I, and I'm simply going to print I, and then the words factorial equals, and then call the factorial function using I to generate all the factorial numbers starting at 0 and ending at 10. So let's run this. And as you can see, 0 factorial, that's my base case, is 1. And then the numbers get successively larger, and it did correctly calculate all the way up through 10 factorial. Now the size of an integer puts a strict limit on the largest number that we can pass to the factorial function. 10 factorial is about as large as we can get without overflowing the size of an integer. Actually, it's a little bit larger than 10, but for illustration purposes, I wanted to show that the numbers do get significantly larger very fast.